Hello and welcome to this webinar on how to ventilate crowded spaces with SimScale. My name is Dr. Nagman Khan. I'm delighted to be joined by my colleague today, Dr. Steve Laney. I'd like to welcome all the attendees to this webinar. Let me quickly introduce SimScale, the company. We are a software company founded in 2012, headquartered in Munich, but with offices worldwide. And we've created the world's first cloud-native engineering simulation platform. Now, what that means is we're enabling every engineer to innovate faster by making high-fidelity engineering simulation truly accessible from everywhere and at any scale. So you can access powerful analysis types, for example, CFD, finite element analysis, thermal analysis, all on a web browser without the need for any hardware. Now, why are we here specifically today talking about ventilation and crowded spaces using SimScale? Well, the point of today's webinar is firstly, we want to understand transmission risk factors and the value of CFD. Now, with everything that's been going on with the recent pandemic, COVID-19, and the increased importance on fresh air, ventilation, we thought it'd be a good idea to show the value of CFD for understanding transmission risk factors, also for simulating ventilation in indoor spaces, and a quick overview of what is engineering simulation in the cloud using SimScale. We'll have a quick Q&A session at the end. Please do use the questions panel on GoToWebinar to start submitting your questions as soon as you have them. I wanted to cover this table because I think it summarizes nicely what we're trying to portray in this webinar. Here's a table of transmission risk factors and the value of CFD. In the first column, you can see a risk factor. In the second column, you can see what the input would be to CFD simulation. And in the third column, you can see what the useful output would be from CFD type simulations. So these risk factors, these have been adapted from a NFEMS webinar and authority, including Professor Noakes et al. You can, in the reference, you can see the full details, but some of the risk factors are proximity, for example, the physical distance between occupants in a space, in a crowded space, enclosure, so what kind of room are you actually in, duration, how long are people spending in that enclosure, what kind of activity is going on, how crowded are the actual spaces, and the ambient environmental conditions. Now, many of these can be represented in a simulated model. For example, we can have a model of a room and simulate people in there, like my colleague Dr. Steve Laney will show shortly. And obviously, we can put in any number of people. They can be seated, they can be standing. We can change the distance between the people as well. Same, we're modeling real rooms and buildings with occupants, with windows. We're simulating HVAC units in there. We can add construction data like thermal properties, U values, infiltration. So, you know, we're creating a realistic representation of the room. And we can look at transient behavior as well. For example, what happens when someone coughs and sneezes using the passive scalar approach. And we can also change metabolic rates of people, which would increase, for example, the CO2 generation. And it's easy to change the 3D model as well, to change, for example, the aspect ratio of the room, facade glazing ratio, the number of people. And of course, we can set the ambient conditions of the temperature in the air, inside and outside. You know, we can set ventilation flow rates. We can simulate an external wind, for example, as well. So some of the outputs you get from this are incredibly useful. So we can look at the airflow in and around occupants. We can look at the airflow distribution within a room. That includes air velocities. It includes temperatures, thermal comfort, thermal stratification. We can look at something called the mean age of air. For example, how long does it take for air to mix in the room? We can look at ventilation efficacy. We can look at CO2 as a measure of air quality and various other things. We can also have a quick look at how varying external conditions might change the indoor room conditions. For example, if you have a room with windows open, an increase in wind speed could radically change the airflow distribution within a space. So these are all really great examples of the value of CFD. And I'm now going to hand over to my colleague, Dr. Steve Laney, to talk us through a real example in the SimScale platform of ventilating crowded spaces. Thank you.
Great. Thank you, Nagman. Let's have a look at the technical project now then. So what metrics can CFD give us? Well, for COVID mitigation strategies, there are some key metrics that are important for any comparative study. And we can obtain all of these from CFD. So one of these, for example, is the whole room ventilation rate, the air changes per hour, also known as the mean age of air, and the ratio of fresh air, the placement of the air supply and the exhaust grills, and the air velocities and air mixing in close proximity to the occupants in the space. So what have we done here? Well, we've taken a template for a standard air quality scenario, and we've generated a CAD model that's publicly available to represent a generic classroom or restaurant environment. And from there, we've looked at the physical and thermal characteristics of this building and set it up so that it is true and correct with the U values, glazing parameters, and accurate physical sizes. We've provided a standard room layout with 4 tables and 4 occupants, and there's openable windows on one of the long facades and 4 roof supplies and extract diffusers. The diffusers can be set up however we want as a variable parameter, and the occupants and the lighting generate heat gains, and there's solar gains applied from the windows. And the CAD model is completely adaptable so that we can run different CFD scenarios, and by leveraging the capabilities of the cloud, we can run hundreds of scenarios in parallel. So let's have a look at how we've used this CAD model to set up some different scenarios. Well, we've taken a baseline first of all, and in this baseline we consider the windows to be closed and that we're supplying a fresh air rate of 10 litres per second per person at ambient temperature through the HVAC system. And it's supplied through 4 diffusers, so a total of 160 litres per second. So an engineer wishing to explore the movement of air and the thermal comfort in the space can then use CFD to optimise the ventilation design and layout. The outputs can aid engineers in assessing the ventilation effectiveness of the space by simulating the mean age of air and visualizing the flow field within the structure. Various configurations of mechanical supply and window alterings can then be run to find the optimum scenario. And that's the great thing about cloud computing here. We can vary all of those parameters like the window opening angle, the supply rate, the position of the diffusers, and all of those simulations can be run in parallel. Okay, so let's have a look at some of the results now in SimScale. For the baseline scenario with the windows closed, we had a mean age of air of about 20 minutes from the air entering the space. So here we are in SimScale. All we're using here is a web browser. That's all you need to access SimScale. And we can see the results of the base case visualized here. At the moment, we're looking at a cutting plane around the diffusers so we can see how the airflow is circulated in the room, see how it comes out of the diffusers and then distributes in the room and around the occupants. So we can get some nice visual analysis of how the room is actually being ventilated. So if we want to analyze this room to see the predicted mean vote or percentage of persons dissatisfied or temperature, we can add different cutting planes. So with this next cutting plane, we've applied this at head height for the sitting occupants at 1.2 meters high. We can see the flow distribution, and at the moment we're viewing the temperature. And we can see that the temperature in this room is an average of 20.29 degrees Celsius, so it's not too bad for room temperature. And we can obviously change what's displayed on this plane so that we can see things like the predicted mean vote of the occupants. So we can see how satisfied the occupants would be. And typically, we would need this to be between -2 and 2 to satisfy the ASHRAE standards. And we can see here that the predicted mean vote would be a little low for the occupants. It's a little on the cool side. And we can obviously also analyze the passive scalar as well, which is the mean age of air. So we've introduced a passive scalar into the room, and this is a measure of how old the air is in the room. And we can see that we've got an average of 1,171 seconds. So the air is relatively old. The ventilation isn't extremely effective. Another way we can obviously measure the passive scalar is to look at averages on outlets. So if we look at the passive scalar value at the outlet, we can see the value at the outlet as well. 1,253 seconds is the average age of the air. Okay, so we've got some basic analysis out of the base case there from the cutting planes. And we may also want to investigate the different regions of the room as well. And to do that, we can use the isovolume. So we could look at where in the room the passive scalar is acceptable. So in this circumstance, we're looking at where it's between 0 and 700. So what we would consider an okay age of air, and it's only concentrated around the diffusers. So that makes sense. That's where the best air is in the room. And we could obviously increase that maximum and see how the isovolume increases and expands out into the room. But we haven't got a great condition here. The mean age of air around the occupants is much higher than we would like it to be. So we've visualized the flow on cutting planes, and we can look at particle traces as well to see how the air is distributed. So that's a quick bit of analysis of the base case, but in this scenario we've actually run many simulations. So we've varied the window opening angle from 9.2 degrees up to 35 degrees. So we can see the geometries that we've used to do that. The base case geometry has the windows closed on both sides. And then in the case with windows open 15 degrees, we can see them open to 15 degrees, all the way up to 45 degrees for the highest window opening angle. So this allows us to investigate how natural convection through the windows will aid the ventilation in the space. So let's have a look at one of these cases with the windows open by 25 degrees so that we can see how that compared. So in this simulation, we can see that the windows are open by 25 degrees, and we can analyze how the airflow has been improved by that. With the particle trace, we can see the airflow coming into the room, circulating and going out of the exhaust. But the key indicator here is the mean age of air, so the passive scalar. So if we use the isovolume again, we can use this as an indication of where we have good, more acceptable air in the space. And now we can see with the isovolume, it occupies a much greater proportion of the room with an acceptable passive scaler. So we've set the range here from 0 to 700. So actually, an easier way of viewing it in this circumstance might be to set it from 700 to the maximum that we see here, 900. So we can see actually the pocket of air which wouldn't be so favourable. And there's much less of it. So we can see at the occupant's head height, they have much better, lower mean age of air to consume at about 700 seconds. We can obviously analyze that with the area average at the outlet again to see the difference that we've got here. So we can see that we've got a mean age of air of about 628 seconds. So it's definitely helped having the windows open. Our project actually isn't complete here though, because we've only run simulations up to the 35 degrees window opening, and we've got a geometry that goes up to 45 degrees open. So let me show you how we can set off another simulation. We can duplicate one of our existing ones and use that as a template so that we can use the same boundary conditions and settings with the new geometry. So we can give it a new name, and then all we have to do is swap the geometry out for our replace geometry with 45 degrees window opening, and SimScale will maintain the original boundary conditions that we had assigned, and all that we need to do is set off a new simulation run. And we can do as many of these in parallel as we like and submit them to the cloud so that we get the results back in the same time it takes to simulate one. So we can see that the run at 25 degrees opening took 126 minutes. So we could run all of these 9 simulations in that 126 minutes. Okay, so what have we done? Well, we've run many simulations in parallel. We've run 9 cases in total. And we've been able to analyze the mean age of air in the room, the average occupant temperature. And you can see all of the runs took about 120 minutes to run. That could have been elapsed time for the whole lot. And we can see that with the increased window opening area, we have a much lower mean age of air. So it would be much more favorable for the occupants to be in these conditions with COVID restrictions. So what could we do next? Well, obviously we could vary many more of the parameters. We could look at a case which we're currently doing now where we've got a much higher density of people in the room. Previously we had 4 tables with 4 occupants at each table, and we've increased that now in the same space, the same restaurant or office, to 9 tables with 4 people at each table. So we'll see how that affects the results. So in summary, you can use CFD on the cloud for rapid air quality modeling. More specifically, a key advantage is the ability to set up and run many different configurations in parallel. This has the advantage of saving time when critical decisions are needed, and it gives the capability to consider a large solution set. Doing this with traditional on-premise software would be very restrictive and would be very time-consuming and costly. Also, an API is available in SimScale that allows you to connect third-party tools for outdoor thermal comfort or analysis of wind pressure coefficients and advanced analysis in external tools. Thank you for your attention. We'd be happy to answer any of your questions.
Steve, thank you so much for that fantastic presentation and the live demo as well. We have a few questions coming in. Should we take a few questions, Steve, from the attendees?
Yeah, that would be great. Let's answer a few questions.
Okay, fantastic. I guess the first generic question is about importing CAD models. Perhaps you could just comment on the different types of models that SimScale can import.
Yeah, definitely. So this is a common question, and SimScale has got a very flexible CAD import capability. SimScale is built on a Parasolid back end for the CAD, but we can import virtually any CAD geometry, so STL files or proprietary files coming from various CAD packages, including packages like Rhino for building modeling as well.
Fantastic. We have another question here from Manuel about determining the flow going in the room through the windows. Now, I know there's several ways of doing this, kind of explicitly and implicitly. What's the best way to do it? How was it done here, given the types of outputs we're looking for?
Yeah, that's a really good question. So this was a decision that we had to make when we set up this simulation. So we had to decide how exactly we would set the windows, and the way we decided to do it was to do it as actually a flow rate per window open area. I don't remember right now off the top of my head exactly what that flow rate per open area was, but the project is shared. You can go in and have a look at the properties that we used. But for example, on the 25 degrees opening one that I showed the analysis of, we had a flow rate of 0.053 meters cubed per second. So what we were looking to approximate there is just from a breeze and normal conditions outside, how there would be some natural air entering the room.
Great. And I think that also generically, because you've created this template model, it's now easy for designers, engineers, facilities people to test different scenarios. You can go in and apply any airflow rate to those windows, or open the windows a little bit more, or close some windows. So that's the whole purpose of this very kind of parametric model, as it were. Am I right, Steve?
Exactly, yeah. So every part of this CAD model and the setup can be a variable that you vary and investigate the outcome.
Yeah. Great. Another question from Jeremy. Thank you, Jeremy. This is about solar modeling, which is a feature that we have, Steve. It's a recent feature. So the question is, when modeling radiative heat gain, is it possible to model the projection of sunlight entering the windows on objects within the room?
It is, yeah. So this is a new feature in SimScale. I'm not actually 100% up to date on the capabilities of this, but you can certainly now model the solar gain from the correct direction where the sun is entering the building, coming in through the windows and heating the surfaces. So yes, we can. In this model that I've set up, I actually used the slightly older functionality because I set this up some weeks ago before we'd completed the solar gain. So it's actually just a wall heat flux on the south side windows. You'll be able to see that if you look at the model, but there is some advanced capability now, exactly as you described.
Yep, just for the benefit of Jeremy and other attendees on this webinar. So SimScale launched some new features on solar modeling. We actually did a live demo of that a few weeks ago, and the recording is available on our website. Perhaps we'll send the link to that recording as well as when we send the follow-up to this event. So Jeremy and the other attendees, we'll send a link to the solar webinar recording, and in that we demo the new features, how to set up solar gain in more detail using climate data, or just entering latitude, longitude, and then it talks you through the different aspects of the solar gain, how it enters the space, how it distributes in the room, and how to post-process and visualize that solar gain as well, and how to extract that in your results. So that's a great question, Jeremy. Thank you, and we'll follow up with further information on that. Steve, you have another question here from Scott, who's asking, is it possible did you, or is it possible to couple the heat transfer with CFD to capture thermal plumes? So this is, with thermal plumes, stratification, drafts. It's a great question.
Yes, yeah. So we can do this. Obviously, at the boundary, if we set a natural convection boundary, then this will take into account the natural buoyancy of the air due to the heat difference.
Thank you, Steve. Steve, I think it's worth elaborating just for a minute on the power of the parallel simulations and the ability to set up and run multiple scenarios. This is such a critical point, and we mentioned it, but I think just to reiterate it for the attendees, why is that so powerful and why is it so important, especially in a study like this?
Yeah, of course. So in a study like this, where it's a relatively large simulation, it's taking a few hours to actually run and compute. If you were to run this on on-premise hardware, you would obviously be limited to the number of cores and memory that you could use. It would likely take a lot longer, so it might be an overnight or a whole day run. You would be very limited to how quickly you could obtain results. You'd have to block out the simulation machine for at least a week to be able to do 7 runs. With SimScale, we can do all of that in parallel on the cloud. So we can actually simulate faster than you could typically with on-premise hardware. It's all being done in the cloud, so you can do it all from your main work machine. Nothing's being blocked on your main machine while those simulations are being run, and it's all done in parallel. So in just the space of a few hours, you would receive the results that would potentially take weeks with a traditional simulation solution. So it's incredibly powerful for these sorts of parameter studies. If you then add in the opportunities that you have with the API in SimScale, you could take this parameter study to the next level, and you could set off even hundreds of simulations programmatically from a Python script that chooses the parameters that you want to investigate, and then you could get a huge number of data points to analyze and find the best design from.
Fantastic. Thank you. Thank you, Steve. Thank you, everyone, for your questions, and thank you to Dr. Steve Laney for the technical presentation and the model you've set up. We have a quick question from Farid about an academic version for research purposes. So Farid, I'll put you in touch with our academic plans coordinator, and we can reach out to you directly about that. So thanks once again for watching this. What we'll do is send a recorded version of this webinar to you if you've registered and you've attended this event. So you'll get that in the next few days. Please get in touch. They will have instructions on how to get in touch with us if you want to discuss any of your projects coming up where you think this might be useful. We'd be happy to speak with you.
Yep, thanks everyone. Goodbye.
Thank you. Bye.